what we have is M, G, and alpha. And this one is now abelian. In fact, maybe most relevant to us is the real numbers, group of real numbers. And it's M act on Hilbert space H. So we form the H values, the L2 space, and then we perform the alpha to S inverse of X applied to Xi of S. This is for X in M. And UG of T Xi of S equal to Xi S minus T. And cross product is the phenomenon generated by these two gadgets, that pi alpha of M, which now acting on this Hilbert space, and then UG of G and the double comitant. Okay. Now, and we had the following VP Xi of S was SP Xi S. It is consistent with the yesterday. No bar. Okay. Then VP pi alpha of X VP does not move anything, but the VP U of S VP star was SP U of S. So scalar multiple US. Okay, U stand for the UG. U, sometime I mean the UG. Okay, so we have G hat acts on the cross product. Called dual action. Okay. Then the operator value we discussed yesterday is the following. When X is a positive element in the cross product, so if it is in the positive part, then you integrate over G hat and alpha hat over P of dx dP. Okay, sometimes it defines bounded operator. Sometimes it doesn't converge, possibly even not to the unbounded operator, just infinite. So we consider that okay, at the same time, if you actually look at this in the numerical term, dP. Then this is the positive function over the G hat. So your integration makes sense. Okay. And you consider only those X positive element which make this integration finite value. Okay. So this norm is bounded. Okay. So you consider only those, okay, as a POE. Then this has the cone inside.
Yep. For every side. For every side.
That condition doesn't make sense.
X is here, positive element, which has the finite value.
For every side.
It is a scalar and you're taking a norm. You've taken an inner product and then you're taking a norm.
This Xi, this is in L2HG, so inner product makes sense.
That is a scalar.
Yeah.
So the integrand is a number.
Yeah,
So
exactly.
what is the norm of the number?
Then that will be the, if this, oh no, excuse me, not a norm. Okay. This is finite value for all Xi in L2A, oh well, we decided to call it K. And okay, if this is finite value for all Xi, it is not difficult to see that this defines a bounded operator. And it belongs to this integral, and so we write it alpha p of x dp of g hat e of x. Okay. Indeed, this is consistent with my book that I wrote, used that one. But here we are. And the way it runs, because you are integrating all over the g hat, so this element belongs to pi alpha of m positive part. Okay? And actually, here is one thing missing to claim is that on this cross product, the fixed point under the dual action is precisely pi alpha of m. Okay, that you have to prove. That is believable, right? Because the many element is written as pi alpha of x of s and the u of s ds, and alpha p of that is then you are moving sp here, introducing sp, and which doesn't move is that in that case this has to be sit on the origin, right? Now no other component, so it is believable. While proving is maybe a bit involved, and the fixed point is precisely so. So in this way, you got operator valued weight. It has the following property: alpha of A, B, A star A, alpha hat is A star E alpha of X, A for all A in the cross product N. Fixed point N. And so, and the phi hat is defined to be phi circle E alpha hat. Of course, in that phi is defined on M, and the pi alpha is exported to the new Hilbert space. So you bring that weight phi along with this pi alpha. So phi is viewed as a weight over pi alpha of m, okay? So that means that possibly what you have is more precise manner is then this is pi alpha inverse. But too much of the notation, that's too heavy, so drop it. Okay, now is the theorem I'm going to state is the following. Well, the definition for phi hat, you don't need to have faithfulness on field. Any normal weight will do. Okay, so omega is normal weight, semi-finite normal weight, is dual to some phi Wm if and only if omega is invariant or p, which is understandable in the board. If it is invariant, it has to be beyond the pi alpha of m. Okay, and now. Well, now we come to the duality, or that's claim 1, claim 2 is m plus alpha, and once again, relative to dual action G hat is isomorphic to M original algebra with L of L2 over G. Now, this one is acting on L2 HG. Now, how about this one? This one is acting on L2 over H G cross G hat, right? And on the other hand, there's a Pontryagin duality or duality, Planchette formula tells you to transform everything into G by 1 cross Fourier inverse transformation, bringing to the L to H G cross G. Okay, so it's not on the G cross G hat. However, this Fourier transform, okay, let me say, under this cross product, this one, M alpha G. What is the generator? The generator is, of course, pi alpha hat circle pi alpha of x, right? This is pi alpha of x cross identity over L2 over G. Right, because G hat does not act on the original pi alpha m. We observe that fixed point. So when you move to the cross product, it does nothing. So it is pi alpha hat of UG of S. That this will be of RS is S. This one it says on the over P twisted by P. So this one is under P. This one was Yeah. Under the Fourier transform, this one is moved to the US tensor. Let me see, VP. Oh, okay. Here, lambda. This is left regular representation. Okay, that's the way it acts on the in this space, and then UP of xi. Oh, this is not that. Is indeed 1 cross 1 cross mu of GP. Mu, remember, mu stands for the multiplication on the G. Okay, so that's the generator. Okay, so that's the G hat. Now, here's so the isomorphism involved here. And those are the generator we needed. So this pi phi of pi alpha of x times 1 will be, I will explain to you what they are. Pi of x, yeah. It's called now what pi of x? Wait a minute. This phi mu carries. Oh yes. Okay, the target space is on this space. Okay, so phi of pi alpha hat of x applied to psi of s. Okay, this will be alpha s inverse of x psi of s. So that's the place goal. And the phi of pi alpha hat of u of s moves to the upright xi of t equal to psi t minus s, and phi of v of p, that's vg of p, upright xi of t equal to t p. Then here the conjugation comes in. That's the way this this algebra is moved to this Hilbert space from here to there. Okay. So I'll tell you the rather sketch of the proof. Okay. No. Oh, yeah. The second product, cross product, is generated by 1 cross U or lambda S cross lambda S on L2 H G cross G. Okay, view this as H cross L2G. Sorry, L2G. So 3 Hilbert spaces. That's one kind. That's a use S. VP 1 cross mu P. And pi alpha hat this is this kind. Now, we move this S pi alpha hat pi, this one we know. Pi alpha is simply this axis. Okay, let's write it here. Here's L2G, another L2G over here. So that's pi alpha of x acting on this this Hilbert space times identity. Okay, remember that alpha hat did nothing on that generator, so this is the generator. Now, we now introduce W to Rs to be psi Rs S. Okay. I call this W operator. This is the definition. Fundamental operator of group G. Why fundamental? If you look at this one, if it is finite group, G cross G, R plus S in the middle, right? That's a multiplication table. So this is W is exactly telling you what the group element does. So this is multiplication reflection of multiplication table in the operator to the operator. So it's the fundamental operator of G makes sense in that regard. Okay. Then let's look at what happened. Okay. W pi alpha of x cross 1 W star psi of Rs equal to pi alpha of x cross 1 W star psi R plus S, which is then that pi alpha x acts on the first element, first R inverse of x, and then W star psi R plus SS. And W star cancel that action, so this will be RS. So we call this operator to be pi of x pi of x acting on Rs. Okay, so now W and the US commute, doesn't it? Because group is commutative, so it does nothing. Also, W and P, okay, VP is doing that scalar multiplication according to the second component. And W does not regard what, where scalar is there or not, right? That is changing a variable. So W commute with V, U, and V. Okay. Yeah. Wait a minute. No, it's not true. W, US, W star, Xi, why don't we write W? RS. Okay, so that's UT, W star, Xi, R plus SS. UT does this, W star, Xi, R plus S plus, okay, W star is not taking T. Excuse me, W, UT was what? UT does this twice, so it's does minus T, S minus T, W star. Then you are now S minus T, take it, so this equal to Xi R S minus T. Okay, so that means this large UT, W star equal to 1 cross lambda G T. So that now we lined it up most of the stuff. Okay, and W and VP commute, that the VP was 1 cross mu G T. Mu G P. W VP W star. Now we are business here. This and that, those two gadgets generate L of L to G, right? That's the uniqueness of Heisenberg commutation relation. It's, okay, this, then that means C cross L of L to G pops up here with W. So using W, using this W, W star is then generated by pi of m is generated by pi of m and pi of m and VP, this one, it generates C cross L infinity of G, and then this lambda G, that's a group algebra. L infinity of G hat. Wait a minute. This one, I'm sorry. This one is generated by this one. Yes. This one. And then this one generates the group algebra R of G. C cross R. C cross RG. Now, what it is, maybe here is you can do more for the exercise now. Pi r. This is indeed equal to, this is equal to this is equal to pi alpha of m tensoring with L infinity of G. This is equal as a set. Okay, so that's what. So this boils down to here. You can see everything is concretely represented now. Okay, so then I think I leave it to you to prove that. Then, if this happened, then pi alpha of m, and now this and that generate L2 of G. And the pi alpha of m is sitting on that three-component Hilbert space. Okay, so that's this is the way to see. And then you chase all the this transformation, then you will see all the other facts I mentioned yesterday. Okay. I think because I'm a bit behind, so I just skip the discussion about the second cohomology. So I move to the Abson spectrum. Okay, so far so good, but still I need to understand how the cross product, etc., look like. So now, as a corollary of this duality theorem, and also another corollary that if you make cross product by modular automorphism, you end up with semi-finite phoneme algebra. And then you had the dual weight, which is scaled by well, the dual weight is left invariant under the dual action alpha. Okay. So when you have M, this is N, and the phi hat, and it's dual weight. And the modular automorphism is then precisely add URT. That's the translation representation of real line we discussed. And so we write this to be add of h to the power it. And the h is the logarithmic generator. Of URT. Writing URT in the exponential ITH. What is h? H is the derivation, the differentiation of degree 1. Once you differentiate it, you exponentiate it, then you get the translation. And indeed, this formula is nothing but the Taylor expansion of the by translation, right? And here h equals to e to the h. So this is kind of differentiation and the exponents, so that h to the power n or divided by n factorial and the summing up. And so that means the differential. Okay, now this tells you that modular homomorphism inner. So you make tau of x to be phi limit epsilon goes to 0 phi of phi hat of h plus 1 minus 1/2 and x h plus epsilon 1 to the minus 1/2. This is bounded positive operator, and this is multiplication inside n. Okay, inside n. So this makes sense. And when epsilon goes to 0, yes, this increases because this is actually same as x1/2 epsilon f1/2. This is the same thing. So this is when epsilon goes to 0, this will increase. So the limit exists. Only question is plus infinity one. The converges to the finite value or not. Okay, so well, you don't expect tau to be finite trace because n, if m is at purely infinite, no trace, type 3, n contains type 3. You cannot expect a finite from number algebra which contains type 3. So you don't expect tau to be finite value. It is plus infinity is inevitable. That much we know. So indeed, if you do this, this is indeed you can guess from here. You are more or less canceling phi by this. So the modular homomorphism of tau, well, indeed, of t is sigma phi hat of t followed by add h to the minus it, and then this goes identity. Okay, so the modular tau is a trace. Indeed, the miracle occurs through all things. This is semi-finite. Faithfulness is not the issue. We know that H is non-singular. It's faithful. So this is But the miracle is this is semi-finite, okay, indeed, and semi-finite faithful trace on M. Now, sigma phi hat, we write, say the S. So dual action, because of this privilege of this theta, that dual action, we gave a special name, not the hat, just theta S, okay? And now we know N theta real line is M tensor product with L of L to R. So within the monitor equivalence, we recover the original algebra. Now, how it moves? Remember the theta S of URT was e to the minus IST URT. Okay, we are talking. That means theta SH of H is e to the minus SH. Wait a minute. I think this is a plus. Otherwise, theta SH this is the matter of convention, which way you take scaling up or scaling down. But I lived on the scaling down so long, I want to make it scaling down. So theta of SH equal to e to the minus SH. Yeah, okay. So that HS to the power IT equal to e to the minus IS T of HIT. Okay, and then see what happened. This applied to the tau. Tau was H to the minus 1/2. Oh, excuse me. Tau circle theta S. Phi hat of H to the minus 1/2 theta S of X H to the minus 1/2, which is theta phi is theta invariant. So you can bring theta S outside. Minus H minus 1/2 X theta S of H minus S 1/2. Right. And this one, we had invariant, so this is, this doesn't count. And the minus gives me the original e to the minus 1/2, e to the minus 1/2, or together tau minus S tau. So theta scales trace down. So you ended up with a system, covariant system over real line with faithful semi-finite trace, which is scaled down by the one parameter domain. And original algebra M is n theta. original algebra is n theta. Okay. Now, since we are moving in this direction, I'll go quite a bit derailing from what I planned. Now, change the point of view. Okay. Suppose you have N, R, theta, and the trace. The gadget is the following. N is semi-finite phenomenon algebra equipped with phase polynomial trace tau, which is translated by this rule. Okay, so tau circle theta s e to the minus s tau. Now, there's a two way to go in this case. Okay, one way is you write M to be n fixed point. Well, what happens is when you have scaling trace down and you have a fixed point, then there exists another one-parameter automorphism group. So, namely, what's happening is the following. There exists one-parameter unitary group such inside N such that, I write T. Theta S of UT equal to e to the minus ST of T. You can find such a unitaries when you have this. I don't say this is a trivial fact, but I will tell you that flavor of it, how you get such a one-parameter unitary group is the following. Okay, first fix the projection E, non-zero. Okay, theta S of E, trace e to the minus SE. Okay, so this is less than 1. So that means that theta S of E, this does not, wait a minute. No. We fixed that 1 value, so use of T. Okay. Now, you repeat theta to N to the positive side of E. Then this goes down, of course, goes down 0. And what you do? Oh, yeah. Then you sum up this theta N T of E. And use okay, the trace of this one is, if you look at this, the summation of this tau, that's the summation of e to the n t times tau v, which is okay, 1 minus e to the t, v minus t of tau v. Okay. This means that this is definitely smaller than that. So, and you take the theta t or n of v. Okay. Because of this, you can get this to be a projection P, and theta t of P become to move to the perpendicularly. Okay, so you can then you can find the spectral measures within n, which transform by this theta nicely, and then you generate one parameter unitary group. All right. Oops. Now, then what miracle occurs is the following. This ut, by no means unique, but add ut, there is phi such that so the fixed point, it becomes modular automorphism on the fixed point, and the original algebra and it becomes isomorphic to that. That's the one way. Another way is, of course, make a cross product right away. No, theta. Oh, okay, why don't we? Of course, this is m. That occurs. Yes.
N cross product term equals n.
Yes, this indeed, this restriction of this one inner automorphism of n to m, then it becomes the modular automorphism on m. And the theta becomes the dual to that. So you are now, of course, this is a bit hard. Okay, you're digging out.
It's not some theorem of Magnus Landstedt.
What?
Is a theorem of Landstedt, isn't?
Theorem of
The
who?
characterization of crossed products.
Yeah.
By the anti-commutational relations.
Yeah. Yeah. This is all depending on the Heisenberg, the uniqueness of Heisenberg commutation relation. Yeah. And now, so, but another miracle, I'm not going to prove it, is the following. M, there's both true. Relative commutant to n is the center of n. Okay, fixed point, the relative commutant becomes the center of n. And now, if you make the N relative commutant within, no, this shouldn't be N, maybe R. In this R, this will be center of M. Center of R. Center of R. So if R happen to be factor, that's the most interesting case. If R is, excuse me, our original algebra M is a factor, then this is a scalar. Oh, no, excuse me, I'm sorry. This is not true. This is true, but N prime in R. Yes, this is the center of R. Yeah, this is the center of R. And this is the center of N. And okay, so I think I will come back to this anyway in a later time. Now let's see. Now let's go back to the plan I planned at the Arbison spectrum. So far, we worked on the cross product. That means going out from original algebra. Now we want to stay within a given system to make the analysis of action of abelian group on M. So the Arbison spectrum okay, we leave phenomenal algebra for a while, just to the abstract Banach space. However, which it says dual to the given, the Banach space. Another vector says the dual. That is precisely the case. And GLW of X is the set of alpha to X such that sigma X star continuous, bicontinuous. So it is 1-to-1, 1-to-1. So alpha, if omega is in X sub star, then omega following alpha is another element in X star. That is the assumption, okay, GLWX. And the action of group, okay, we keep group G locally compact abelian. As I told you, the real line is our actual object. So S in G goes to alpha S to GLWX, and the supremum of norm of alpha S is bounded. And of course, the group rule is observed, okay, preserved alpha. Okay, those are the objects. So x of star, g, and alpha. Well, with this abstract setting, what we can do? Well, we can do to prepare the languages. Okay, now, when you have group G, then L1 of G is Banach algebra. F convolution G of S equal to F of T, G of T minus S minus T dt. And the involution, well, we are not much concerned about the involution, but F of minus S. Okay. Then what happens is when you apply F Fourier transform, F of S ds over G, P in G hat. Okay, the holometry. Then what happens is this Fourier transform is F of L1 of G goes to Fourier algebra. Okay, this is C naught of G hat, the continuous function vanishing at the infinity. That's a Riemann theorem. And so this is continuous. And however, unfortunately, it's not all of them. It's A of G hat and called Fourier algebra. Okay, convolution F star G equal to pointwise multiplication of Fourier transform. Okay, so we are interested in this one. Okay, but if you apply F to the intersection of L1G, also the integrable relatively scale integral, then this is A of G goes into A of G hat intersecting L2 of G hat. And miracle happens, there is a measure dp on G hat so that F of F2 norm equal to the original norm. And because of that, isometry. And the range is dense on the target space. Indeed, actually, if F is in L2 of G, then this integral K SP Fs ds, this converges. And when K's compact set increases to the G, then this converges to extended Fourier transform of F in L2, in the L2G sense, not pointwise convergence, okay? L2 sense. So this increases to the, and so that's the Fourier transform, and the Fourier inverse transform is usually taken as adjoint. So P of S is taken this is only true for L1 over G hat relative to the measure which is, guarantees the Plancherel formula. The Plancherel formula is this one. Okay, so F hat is different, slightly different from this. And indeed, what happened is F hat following F is identity on L2 over G, and this one, this one is extended one, and this one is F indeed adjoint. And the same is true. But if you will go beyond the L2, then this becomes a very delicate problem. Yes. That you consult with hard analyst. Now, so with this much of a preparation, just like Servan did this morning, F over L1 over G allows you integrate alpha of S F ds over G. Okay, it's called, well, I hesitate to call this a bit of confusing than F. And because of this, if you follow alpha F, then you will very quickly realize, because alpha, maybe you want to see D, then alpha T plus S, or S plus T, change variable S minus T. So this is lambda sub T to the F. And we know that lambda TF minus F, one norm goes to 0 as T goes to 0. That's continuous in L1. Translation is continuous on L1 pointwise. If you fix the L1 function, that's transformed nicely there. Okay. In the case, if this is a real line, and if F is a real, the analytic, if has analytic extension, then thanks to this, this has analytic extension as well. In the event of a real line. Okay. Now, but what we are going to do is the following. For F hat, we want F hat in A of G hat. Then you have F. It's coming from L1 through Fourier transform. And I write alpha F as alpha F hat. Okay, it's alpha F hat is not integration. So you want to find out the origin of F hat in L1 function, then integrate. But what's nice about it is the following. Okay, alpha F follow alpha G is precisely convolution. But in this notation, alpha hat f, alpha g hat equal to alpha pointwise multiplication. All right. So in other words, this A of G hat Fourier algebra. This is abelian Banach algebra. Where the norm from? Not from here. It's not a closed, but original L1 norm. Original L1 norm gives you A of G natural norm. And so from here, F hat to alpha F hat, which is then bounded linear transformation in L of X. Commutative ring, okay, and the function algebra over G hat acts on Banach space X. So the spectrum of A of G hat is precisely G hat. So now you fix X in X. I alpha of X is those function F hat in A of G hat such that alpha F hat of X equal to 0. Okay. Of course, then I alpha of X with A of G hat closed ideal of AG hat, Fourier algebra is closed. Then you have the 0-point set of ideal. There's a so the hull is called the hull. Hull of I alpha X is 0-point set of this ideal. It's subset, closed subset. This is the one we call the spectrum X relative to action alpha. Okay, a little bit twisted around. You might fear because it's direct. It's not directly integrating. When you go back to the original G and integrating and etc. But now let's look at example of what is this spectrum of alpha? It ought to be. Suppose you have following mapping from G hat into X over P in X, capital X, such that alpha S of X of P equal to SP X of P. See what happened. Okay. And you assume that the norm of XP is integrable over G hat, so you have another element in X. Okay? And then see what happened. Maybe it's good to have it. It's because null set, etc. is no. We don't want to deal with this continuous with compact support. Say with compact support. So in other words, this X is in C of X from G hat. Right? So you can integrate and with particular condition, this. Oh, no. This is a finite. That's what it is. And define, in that case, you can define x to be g hat x of p dp exists in the x. Okay, that makes sense. If you are not comfortable, you test against element in X predio. Then you can see this. This makes sense. Now, see what happened. What happened? The action alpha s of x. Integral of xp dp. That's alpha s x of p ds. That is then, by assumption, sp xp. This is dp. Okay. So this is what's happening. Now, what is IR x in this for this particular x? IR x with those f hat such that alpha f hat of x equal to 0. Right? So to examine that, so alpha f hat of x is alpha f hat of integral over x of p dp. However, this is the integral of f s. We move f hat. This is alpha. Okay, f of s. This is integral over g. F of s, alpha of s, applied to x of p dp ds. That's the how the alpha f hat defined. So let's move on. So this is g hat. G cross g hat. F of s. Alpha s of x of p dp ds. Then this one is, you change the order of, well, here you have SP, XP. So then you change the order of this. That means equal to SP FS DS XP dp. Then this is probably we made a mistake there in the defining this one. because, okay, any case, we have this one is Fourier check inverse transformation f of p x of p dp. Okay, this means that I alpha of x is those function f hat such that this would be that f hat minus p equal to is 0 equal to 0 on the support of x. So maybe I should take not f check instead that f inverse transform, so that the notation has to match up, right? So instead of this, you want to have that one, f hat of p equal to 0. So that so this means that how spectrum is precisely then support of that function x. In other words, that the spectrum alpha of x is kind of oscillation mode of x under alpha. Okay? So, yeah, it's because Fourier transform, Fourier inverse transform are not the same formula. We have to, I twisted my arm. Okay, so we should take f hat instead. Okay, now where are we? Oh yes, we should. I should set up all the notation. So please revise the spectrum alpha of x. Okay, this is the how of I alpha of x, and the alpha f hat is alpha integration of f check of s alpha s ds over g. Yeah. Fourier inverse transform of f check equal to f hat. Okay. Because the duality is not mode 2, mode 4, those confusions all is unavoidable. Okay, now for subset, closed subset in G hat, x alpha of E is those x in X such that the spectrum alpha of X is contained in E. Okay. Now where are we now? Okay. Now the spectrum of alpha is the hull, the 0-point set of the set F hat in G hat such that alpha F hat equal to 0. So this is called Abson spectrum. The one thing important is that spectrum alpha of alpha f x equal to subset support of f hat intersection spectrum alpha of x. Okay. Okay, those are the notation we need. Okay. Okay, next time, with this much of a preparation, it's 2 minutes. Okay, why don't I state the theorem itself? Because I don't want to redefine the notations. Okay. Abson spectrum is it has the following. To some extent, those subspaces X alpha E determine the action. Theorem suppose X starts before and alpha beta action of G. Then following is the equivalent. 1. X alpha V, X alpha or beta of E for all E compact subset of G hat. And then second, X alpha V contains X beta of A. Same. Number 3, alpha equal to beta. Those are the equivalent, the Abson theorem. Of course, alpha equal to beta means alpha S equal to beta S for all S in G. Okay, so that this is a tool. And then with this theorem, he has another theorem, which I'm going to discuss next time to begin. Okay. And now, what's needed is then apply Abson spectral analysis to the modular automorphism and see what's really happening in a phenomenological algebra relative to the modular automorphism.